And this is our 7th lecture in Basics of Hemodynamics. With this lecture here, we'll learn about the Bernoulli equation and the relationship that exists between velocities and pressure. We'll establish the limitations of using the pressure gradient calculations in echo. We'll understand the pressure recovery phenomenon, specifically with prosthetic valves. And we'll use the pressure gradient to determine pulmonary artery systolic pressure, a very common measurement we do in echo. One of the simplest applications of pulse wave and continuous wave Doppler is the use of velocities obtained to derive pressure gradients between two chambers of the heart. But how did this come about? Basically with the Bernoulli equation. A change in pressure is equal to the sum of convection acceleration, flow acceleration, and viscous friction. Now fortunately this can be simplified. We are investigating peak flows, thus acceleration is effectively non-existent at peak. Blood velocity and blood viscosity influence viscous friction. These play a negligible effect when the orifice is greater than 0.25 centimeters squared. Pretty much everything cardiac. And thus this can be ignored as well. This just leaves convective acceleration. Thus we have a much more manageable calculation now. When we consider the density of blood, P, the calculation is displayed as what you recognize here. Now, in many instances of cardiac imaging, V1 is minimal, less than 1 meters per second, and thus plays a negligible effect when V2 is large, such as 64 minus 1 bears little significance to the result. So our calculation can be simplified further, just as simply 4V squared. It is important to note that this does not define the pressure itself, but the pressure gradient as stated, the change in pressure between two areas. Significant viscous forces will affect the outcome of the formula. Viscous friction we consider to be negligible and not play a part in the simplified equation. However, in cases where blood density changes, we should be wary. Severe anemia will lead to a decreased density, and increased red blood cell count in such as polycythemia leads to increased density. The error that arises from this can actually be significant, in the order of around about 20%. These viscous friction can also have significant impact when considering the evaluation of long tortuous muscle septal defects, or long coarctations. In these instances, significant energy is lost through the travel of a long obstruction, which will lead to an underestimation of the true gradient. If the sonographer does not attain parallel beam alignment with the flow, then underestimation of gradients will be attained. Consider the Doppler equation that we have here. So we can see that cos theta plays a part of what we're actually looking at. But in cardiac ultrasound, we don't apply cos theta. We always assume you'll get parallel alignment. So here I'll actually discuss a little bit more about cos theta and why it's not part of cardiac imaging. Notice how at 0 degrees, cos is equal to 1. And at 90 degrees, cos is equal to 0. Effectively showing no Doppler shift. If we were to plot a graph, it's not a direct line between the two. It looks more like a curve, as we can see on the screen here. Notice as we get beyond 20 degrees, the angle significantly affects the Doppler shift, so it is underestimated. So an acceptable transition point is 20 degrees, which is up to 94% of the true value. Thus, in cardiac, we aim to keep this angle of incidence minimal when we line up our Doppler profiles. So why don't we apply angle correction? This is because it introduces another potential error into our calculations. It has been established that inter-observer variability is very high, and that applying the same angle is not particularly reproducible. It is assumed that sonographer will appropriately modify the image to align the parallel flow. Thus, not to do so would lead to a significant underestimation in velocities. Flow acceleration is presented as V1 in the modified calculation, and may be significant in some instances. This may be due to a coarctation, systolic flow obstruction in the left ventricular outflow tract, or increased cardiac outputs as examples. An example may be necessary to include V1 when the aorta in the presence of coarctation. The velocity may easily be higher than that of 1 meter per second, and the coarctation itself relatively mild. Thus, by excluding V1, the pressure gradient is significantly overestimated. Another example may be where blood leaving the heart and into the aorta. The blood flow in the LVOT may be significant in relation to the flow through the aortic valve. In this example here, we have a flow through the aorta of 3 meters per second and flow through the LVOT of 2 meters per second. There is basically a 45% error if V1 is not considered, as we can see in the calculation here, of 4V squared minus 4V squared of V1 is 20. But if we didn't include V1 and just had the 4V squared, of which is 9 times 4, 36. So significant error. Furthermore, there may be significant flow acceleration prosthetic to a prosthetic valve, as increased force is required to push the valve open. As this component is ignored in that simplified equation, it would lead to an underestimation of the gradient. Prosthetic valves present challenges in their assessment. Their construction may lead to the presentation of significant artifact, including signal dropout, and thus the sonographer may not attain the optimal velocity, alignment, or sample positioning. Valves such as bileaflet tilting discs have different velocities and areas of the valve. When the valve is open, the orifice between the leaflets is smaller, with higher velocities compared to the flow going over the leaflets, as we can imagine here. Higher velocities here, lower velocities there. Typically, we cannot isolate one velocity from another, so we attain a slightly overestimate of the average velocity through the valve. The phenomenon of pressure recovery also has impact for prosthetic valves. When the sonographer investigates pressure gradients, we assess blood moving with low pressure and high velocity, moving through the valve, transitioning to a relatively high pressure with low velocity. This transition is abrupt with a prosthetic valve compared to a native valve, where the transition is more gradual. This in turn may lead to an overestimation of true gradients. For those who work both in the catheter laboratory and in the echo clinic, they may see discrepancies in a patient with catheter and echo-derived pressure gradients, specifically with aortic stenosis. This is also related to the pressure recovery concept detailed just previously. In the cath lab, the cardiologist pulls the wire back from the ventricle into the aorta, and what is recorded is two separate measurements, peak aortic and peak LV gradients. This peak-to-peak method value is simply a derivation of the largest value in the left ventricle minus the lesser aortic. It's a non-physiological measurement as the readings cannot be made instantaneously. Reviewing the pressure waveforms, we can see that aortic peak pressure occurs after that of the left ventricle. So left ventricle peaking here, aortic peaking here. This is because the left ventricle needs to generate significant force to push blood through the narrow orifice of the aortic valve. In echo, the Doppler measurement of a peak gradient is an instantaneous measurement of change between the left ventricle and the aorta. Again, reviewing the pressure gradient graphs, we see the gradient attained by echo will be higher than that by catheter. So a peak to peak by echo would be here to here. What does correlate well with catheter-derived measurement is the mean pressure gradient by echo. A hemodynamic measurement we'll cover shortly. One of the most common applications is the determination of pulmonary artery systolic pressure. We safely make the assumption that pulmonary artery systolic pressure is equal to right ventricular systolic pressure in the absence of pulmonary stenosis. By investigating a tricuspid regurgitant jet, we align as parallel as possible with the beam. We can work out the pressure gradient between the right atrium and the right ventricle. So a 4VR squared of the TR jet also needs to account for the receiving chamber. Thus, the calculation becomes 4VR squared of the tricuspid regurgitant jet plus right atrial pressure. But how is right atrial pressure derived? The sonographer assesses the IVC visually. The inferior vena cava connects to the right atrium, and thus it's a good representation of pressure in the right atrium. The large vein acts as a reservoir, and with relatively low muscle fiber content, its walls are very compliant. Breathing changes intrathoracic pressures and venous return. A breath in increases return and causes the vessel to collapse, and expiration has the opposite effect. Both its size and compliance with expiration are utilized to estimate the right atrial pressure. Minimal variation may be seen at rest, and on occasion, a short, sharp sniff is required by the patient to exaggerate this effect and demonstrate a more obvious collapse. As the IVC and the aorta run parallel to each other, it is important to distinguish the two. The aorta is medially positioned, pulsatile, and not affected by respiration. And by applying colour to the subcostal window, we'll show red blood flow, direction of blood moving towards the probe. The IVC is slightly laterally positioned, less likely to be pulsatile, may have respiratory variation, and will show blue flow, blood moving away from the probe towards the heart. So here we have a table that estimates right atrial pressures depending on what we're actually seeing. So when we see that the IVC size is normal, less than 2.1 centimeters, and has a greater than 50% respiratory change, we give it a right atrial pressure of 3. When the IVC is greater than 2.1, but still has greater than 50% collapse, 8 millimeters of mercury. Or if the IVC is normal size, but has less than 50% collapse, then we'll give it 8. If it's enlarged and less than 50% collapse, 15. If it's significantly dilated, if it has reduced or no change at all, 20. And then if it is significantly dilated in the presence of severe tricuspid regurgitation and there's no change in the size, then we'll markedly increase the right atrial pressure to 24 millimeters of mercury. The final value is often used when there's free tricuspid regurgitation as a result of lack of coaptation from the leaflets. It is often seen that there are low velocities in instances from the tricuspid regurgitant jet, even though there is significantly strong signal. This is because there is a markedly increased right atrial pressure with a reduced pressure gradient between it and the right ventricle. Therefore, it is important to note that the strength of the signal does not indicate that the velocities that will be attained. When a patient is on a respirator, there is active driving of air into the patient, and the right atrial pressure cannot be estimated by this method. Consider if the patient has pulmonary stenosis. The right ventricle must work harder to overcome the stenosis, and thus right ventricular systolic pressure does not equal pulmonary artery systolic pressure. To apply the previously mentioned formula would overestimate the severity of pulmonary pressures. This gradient must be accounted for, so the formula now looks like this. Right ventricular systolic pressure is equal to 4v squared of tricuspid regurgitation minus the 4v squared of the velocities moving through the pulmonary valve plus the right atrial pressure. Also consider that there are other methods that may be utilized to measure the pulmonary artery systolic pressure. In the presence of a ventricular septal defect, we assess the pressure gradient between the left ventricle and right ventricle. By recording systolic blood pressure, we can manipulate the simplified Bernoulli 2. Right ventricular systolic pressure is equal to left ventricular systolic pressure minus 4v squared of the velocity through the VSD. This is plausible if there is no LVOT obstruction or coarctation in the left arm, which is used for BP. However, the measurement, unless the patient is monitored, cannot be made instantaneously. Another option is to use a patent ductus arteriosus. The sonographer assesses a pressure gradient between the aorta and the pulmonary artery. So thus, our formula looks like pulmonary artery systolic pressure is equal to the aortic systolic pressure minus 4v squared of velocity moving through the PDA. So aortic systolic pressure, basically systolic blood pressure taken from a BP. Secondary findings may be associated with significant pulmonary hypertension. The sonographer may observe with TD dilatation of the main pulmonary artery and left and right branches, dilatation of the right ventricle, right ventricular hypertrophy, RV systolic dysfunction, dilated right atrium, dilated IVC with reduced respiratory collapse. Severe primary hypertension may demonstrate an RV pressure overload with the ventricular septal flattening in systole. Hemodynamically, there may be a peaked shape to the forward flow through the pulmonary valve, and the flow duration may be shorter than expected. And in our table here, we also have a set of values for pulmonary hypertension, ranging from mild to severe in millimeters of mercury. The pulmonary artery end diastolic pressure may be calculated in a similar method. A high end diastolic pressure will indeed indicate primary hypertension in an individual. The flow assessed will be represented with the pressure gradient between the pulmonary artery and the right ventricle at end diastole. Mathematically, this is written as pulmonary artery end diastolic pressure is 4V squared of the pulmonary regurgitation plus the right ventricular end diastolic pressure. Given the absence of tricuspid stenosis, RV-EDP will be equal to right atrial pressure. So the formula becomes modified to 4V squared of the pulmonary regurgitation plus right atrial pressure. In summary, the Bernoulli has many applications in echo for determining pressure within the chambers of heart or vessels. There are complications when assessing pressure gradients with prosthetic valves that must be taken into consideration. We have explored the use of pressure gradients for determining pulmonary artery systolic pressure and where some of these limitations exist. And there are various methods for determining pulmonary artery systolic pressure, and all of them can be explored in the clinical environment.